right. Nice to see you all. Today we're going to be doing a section of work called KC, Le Chatelier, the equilibrium constant. This is work for grade 10s and 11s, but it's really quite difficult work. I don't know what you guys think. Now I'm just trying to get my screen to... I'm just trying to get my screen to behave itself. So are you guys ready for a real mental workout today? Okay.
Mustafa says no, so.
Who says no?
Mustafa.
Okay, well, we'll just have to make do with whatever we get, eh?
Yes, sir.
Okay, so today we're going to be doing some cooking. Okay, so to do some cooking, I hope you can see I've got a waffle maker here. I'm just going to plug it in. I think you can see the little light is coming on. We're going to make a waffle. So I want you to please, this is very important science. I want you to take down the recipe. So my whole goal, so please take down the recipe. My whole goal for the next few minutes is not to spill on my computer. So here I have a cup of milk. Okay, 1 cup of milk.
Sir,
Yeah.
did sir say take down the recipe?
Yeah, please take down the recipe. Okay, what have I got here? 1 egg. One egg.
1 cup of milk. 1 cup equals
So that was 1 cup of milk, 1 egg, 1 cup of flour.
So, raising flour or plain flour, sir?
Plain flour. Okay, here we've got some baking powder. 2 teaspoons of baking powder. So you got to make sure do you see how your teaspoon's got to be very level? Okay, so two teaspoons of baking powder. And lastly, as I say, I'm trying my best not to spill this on the computer. 3 tablespoons of oil. 1. Now the 3rd tablespoon I'm going to do the following with. I've got to take a paper towel and I've got to grease the paper with. Okay, so there's your 3rd tablespoon. So I've got to grease the machine with it.
Oh, you throw 2 tablespoons in the batter and in the last tablespoon.
So just 2 tablespoons and grease it to butter.
Yeah, you grease it to the 3rd tablespoon of oil. There's 3 tablespoons of oil. 2 of it go into the batter, 1 of it grease the machine.
So 2 tablespoons.
Yeah, in the batter. And it's all yeah.
Also, then he's gonna bring us Tuesday. Also, is the chocolate Thursday?
What?
Also, is the chocolate Thursday?
I call it.
Also, is the chocolate Thursday?
Sir,
Yeah.
this is still part of the lesson, right?
Just say that again.
This is still part of the lesson, right?
Yeah, this is the lesson.
This one. Take it down.
Okay, guys, I'm gonna have to modify the recipe. It's gonna have to be 1.5 cups of flour because I can see it's a bit runny.
But disrespect
Okay, and I'm gonna have to add another teaspoon of baking powder. Okay, so it's 1.5 cups of flour and 3 teaspoons of baking powder. Now it looks good. It looked a bit too runny before. Okay, now we're ready to pour it on. So here's my 3rd tablespoon of oil. I'm just dabbing it on.
No, not like that. I did it. I'll explain it again. So that's
Right, let's pour some on. And now we cook it for 5 minutes.
5 minutes.
Let's time it. 5 minutes. Okay. If you didn't get that, let me just share the recipe with you online. I'm going to go to sharing or presenting. Okay, so here is the recipe. 1.5 cups flour, 3 teaspoons baking powder, 3 tablespoons of oil, 1 egg, and 1 cup of milk, and we're going to get 3 waffles out of it. Can you all see that? Now, could I ask you, if you don't mind, to take down this table?
So can you perhaps zoom in,
Sure.
please? Then we make the waffle recipe.
A waffle.
Yeah, we're making waffles.
No waffles.
You gave us the whole recipe.
I still got my own recipe though. Sorry? Can I?
Isa coming to school on this. No, why didn't you do it yet?
I'm coming to school on Thursday.
So I have a question. So
Yeah.
why did you not do this experiment on Thursday?
Do you know what we in many years we do this. It's just with the COVID, how does one share waffles without
So you put it here and then everyone just come collect the waffles. Simple. Simple.
Okay, I'll tell you what I'll do. We'll do that if it's possible to do it safely.
Yes, sir.
Okay. So have you got this table down?
No, sir.
Okay, so you must get equation or recipe, ratio, start, use, produce, end, and concentration is number over volume. Number over volume. Number of moles, but we're doing this table for waffles. Okay, will you guys then write the ratios in this row? Like 1,5, 3, etc. Just fill in the rest.
Anis, can you please put up your mic?
You tell him, Ezra. Okay, has everybody got the table down? Okay, so let's get the ratios. This would be a 3, a 1, a 1, and we're expecting 3 waffles. Now let's just suppose that all in all, I start with 6 cups of flour. I've got a maximum of 6 teaspoons of baking powder in the house. I've got a matter of 6 tablespoons of oil in the house. I've got 6 eggs in the house. And I've got 6 cups of milk in the house. That's it. I've got equal amounts of all of those ingredients. Okay. Now, I want you to ask yourself, of those ingredients, which do you think will run out first?
Oil. I say the weakest is the flour. Mustafa says the oil.
Okay, so which is the limiting reagent or limiting ingredient? Am I going to run out of flour? Oh, wait, I mustn't forget about my waffle. Whoa. Okay, I just want to go back to this screen. Can you see the waffle maker?
Yes, sir.
So Here's the waffle. Here's the waffle. Hope you can see it. Looks pretty nice. It produces 1, 2, 3, 4, 5. And then I'm going to put a bit of jam on it. I'm going to put a bit of jam on it and a bit of cream. And there we go. Cream. But I think it'd be very rude for me to eat in front of you. But I wanted to show you that our waffle recipe works. It's actually quite nice and stiff, and I didn't get flour all over the computer. So that's great. Okay. So which ingredient will run out first? So to make 3 waffles, I've used that amount. So which ingredient looks the closest to running out?
Maybe the flour. That's what the maker said, sir. Aiden says baking powder.
Okay, ask Aiden why he says baking powder.
Mustafa says the oil. Why do you say baking powder? Aiden, why do you say baking powder?
Okay, with this amount of baking powder, 6 teaspoons, how many waffles could I make?
You can make it. See?
6.
Yeah, 3 makes
6.
3. So 6 would make. So 6 would make 6. Okay, look at the oil. 3 makes 3. 6 would make 6.
Oil is exactly.
But look at this.
6.
I've only used 1 egg, but I've used half my baking powder and oil. So I could make 5 more batches of with my milk and eggs. I've only used 1/6, but here I've used 1/2, and here I've used 1/4 of my ingredients. So is it clear that what's limiting me is my oil and baking powder? Is that clear to everybody?
Yes, sir.
Okay, so
Yes, sir.
so what will run out first? Baking powder and oil.
Baking powder.
Okay. Now let's suppose out of all of this, I'm only going to make 1 batch. That means I'm going to make 3 waffles and then I'm going to be satisfied. So let's say how much of, I'm finished baking now. How much of this have I used in the process of what I started with? How much have I used? So let's start with the flour. How much flour did I use? How much flour did I use, Ezra? Look at the recipe.
1.5.
1.5. And I started with 6 cups. So Ezra, ask them how much I end with.
4.5.
Lovely, 4.5. Whoops. I end with 4,5 cups of flour left. Okay, how much baking powder did I use?
3 teaspoons.
And how much did I end with?
3.
3. So some people like to put a minus here, and then they just say 6 minus that equals that. 6 minus that equals that. I'm not so sure I like that. But anyway. Okay, won't you do the rest? Do the same for the rest here. Okay, so I used 3 tablespoons of oil, 1 egg, 1 cup of milk, and I produced 3 waffles out of that mixture. So I started with 6, I used 3, so I end with 3. I started with 6 eggs, I used 1 minus 1 gives me 5 eggs. I started with 6 cups of milk. I used 1 cup, so I end with 5 cups of milk. Now, how many waffles did I start with? At the start, how many waffles were there? Before I started. At the start of the lesson, how many waffles
3.
were there? Sorry?
0.
0.
0.
And I made plus 3.
1.
So I ended with 3. Okay, now let's get to concentration, this last column. I am making waffles for my family because I'm an unselfish person. So let's say the number of people that I've got to make for is 3 people. So what is the concentrations of waffles per person? That's going to be this number that I'm left with, 3 waffles, number I'm left with at the end, divided by the volume or the number of people. So anyone know what the concentration of waffles per person is going to be? Anyone? I'll explain that again. The volume is
Matthew said 1.
yeah, there we go. So it's going to be 3 waffles divided by 3 people gives me a concentration of waffles of 1. Now, all the leftover ingredients belong to the 3 as well. So I could do the same for all of these. I could say the concentration of these at the end is going to be here. It's going to be 4,5 cups divided by 3 equals 4.5 divided by 3. Yeah, 1.5 each. So each person will be left over and they can go home with 1.5 cups. 3 divided by 3 equals 1 teaspoon of baking powder is left for each person. 3 tablespoons of oil divided by 3 equals 1 tablespoon of oil left per person. 5 divided by 3 is going to be, how many eggs is each person going to take home? 5 divided by 3, 1.66. And the same thing, 5 divided by 3, they're all going to get 1 and 2/3 cup of milk to take home. Is that easy enough, folks? Easy enough?
Yes, sir.
Okay. Now we come to something called percentage yield. Equals how much did I produce out of the total possible times 100. So what was the total possible amount of waffles I could have made in with all these ingredients? What do you think is the total possible number of waffles I could have produced? Any ideas?
Mustafa says 3.
Well, I produced 3, but didn't I have ingredients to produce more? Couldn't I have produced more?
6.
Did you say that, Anise?
Yeah.
Okay, you promoted to matric. Can you explain to us why?
Amount of ingredients that was still left over and that was used.
Right, so I've still got enough teaspoons to make another batch of 3 waffles. I've got enough oil to make for 3 waffles. I've got enough eggs, milk, flour. But the limit is going to be my limiting reagent. It limits me to make another 3. So I've made a total of 3 divided by 6 times 100 equals 50% yield. Does everybody understand that?
Yes, sir. Oh, the awesome sir can explain it one more time.
Okay.
Please.
So the first thing you got to do is look at your limiting reagent. That's why I wrote it there. And so we only have to look at what we got the least of. The least we've got is our baking powder and oil. Luckily, they both equal amounts of the least. So looking at it, we used 3, we had 6, we ended with 3. But that means we can make another batch. The same with the oil. But it doesn't, that limits us, because although we got lots of flour, lots of eggs, lots of milk, because these are our limiting reagents, we're limited. We can never make more than 6 waffles. I hope everybody sees that.
Yes, sir.
Okay, so you take the total you made over the total possible number, turn it to a percentage by timesing 100, and you find that we've got a percentage yield of 50% for this whole equation. Okay. Now, I'm going to...
Sir, can you just pause? Some people want to write it down.
Okay. Now, you guys are familiar with this KC. Okay, well, you just tell me, Ezra, when they've written it down. I will just eat waffles in the meantime. Don't worry. I hope you can't see me eating waffles.
So Mustafa asked if you have maple syrup.
Tell her, unfortunately, due to the lockdown, I don't. I've got to use apricot jam.
Oh, it's done. Okay, so we're done writing. So you can continue.
Okay. Now, there's something called the equilibrium constant. It means after you've done everything, it's somewhat like percentage yield. Somewhat, but slightly different. We make a formula called the KC formula. And it's products over reactants concentration. So we go to this last column here, last column, and we put in that number, which is your product. Okay, so we type this. What is the concentration of waffles?
1.
1. And you have to raise it to the power of 3. I don't know how I can write that on this. I'm just going to have to type a 3 there, but it's supposed to be raised to the power of 3. Divided by, okay, now we got to type in all these ingredients, all the reactants raised to their powers. Okay, so let's start with the flour. What was the flour's concentration? 1,5 raised to the power of 1,5.
Raise to the power of
Times. Here, what's the concentration of baking powder? 1. Now you got to put it in square bracket. That means concentration. What is its coefficient in the formula? 3. So it's got to be raised to the power of 3. Times. What's the oil concentration? 1.
1.
Raised to the power of 3.
3.
Now we come to our eggs. Times. The concentration of eggs is 1,66 raised to the power of 1, which we don't have to write raised to the power of 1. Times, because it's the same answer. What's our milk? Concentration 1,66 raised to the power of 1. And there is what our Kc for this reaction would be. So it's a formula that sort of gives you the ratio of products to reactants. In other words, how much waffles per ingredient did we produce? Shall we just try and work out what that comes to? Okay, so 1 raised to the power of 3 is 1 divided by, let's just see. Now, how do you raise something exponential 1.5? Guys, I'm going to have to leave you to do the maths here. How do we raise? I'm not sure how, but normally we don't end up, we never have coefficients that are 0.5, but we did in this case. You know how we would solve that problem? We would double all of those ratios. That's how we would normally get rid of the exponential 1.5. Does anybody know how to raise something to the power of 1.5?
I just have to do my calculations. I got one comma. Yeah. What did you get? What?
If you multiply all the time, I mean, multiply it by that number, 1.5 of that number.
Huh?
Use your calculator.
I typed out in my calculator. One.
Yeah, 0.198. Other one you can. Why did you get that?
Okay. So what I would probably do is I would double all those numbers, and then we don't end up with an exponential that is raised to the power of 1.5. So, so that is probably how we could get around that problem. So I would, to get rid of 1.5 cups of flour, I'd say 3 cups of flour, 6 cups of this, 6 of that, 2 of that, 2 of that produces 6 of those. And then I would use those coefficients. So if I were to do that, let's just change that. That would be 1 to the power of 3, doubling that. This would be 1.5 to the power of 3. Sorry, that would be 3.
Just changing the numbers now.
That would be to the power of 6, sorry. That would be to the power of 3. That would be to the power of 6. That would be to the power of 6. And doubling those, that would be to the power of 2. And to the power of 2. That's doubling all the ingredients. And now it's easy enough to work out. Okay, 1 raised to the power of 6 is just 1 still. 1 times 1 times 1 times 1, 6 times. Divided by okay, 1.5 times 1.5 times 1.5 plus 1 to the power of 6 is still 1. 1 to the power of 6 is 1. That would be 1.66 times 1.66 plus 1.66 times 1.66. Okay, let's do it. Let's get an answer because I'm curious. Okay, so I get 1 divided by 25.63. Which I get 0.03. Maybe my maths is a bit 0.039. Did you get all of that adds up to 25?
Huh?
1.5 cubed plus times 1 times 1 times 1.6 squared times 1.6 squared. Anyway, that's what I get as the answer. Anyone like to confirm they got that?
Yes, sir.
Great. Fantastic. Okay, so if this number is very small, what it means is we didn't produce very much waffles for the amount of reactants that we had. So if the bigger that number is, the more waffles per product, ingredients that we started with. So that KC is just a number, it doesn't have a unit. It's a ratio of products over reactants. Okay, so this would be considered a small KC, which means we didn't produce much waffle for all the ingredients that we had. Everyone happy?
Yes.
Okay. Now, hoping that you understand it for waffles, I'm hoping that we can do the same thing for chemistry. And so you're not intimidated by it. You see that this is almost exactly the same thing as doing it for waffles. Okay, so let's have a look. This is from November 2019. I don't think I've done this with you, have I? You haven't seen this before.
No, sir.
Okay. Initially, 60.8 grams of pure carbon dioxide is reacted with carbon. So this is like flour and baking powder in a sealed container of volume 3. That means 3 decimeter cube. It's going to be divided by 3 people at the end. The reaction reaches equilibrium at a temperature according to the following equation. Now, equilibrium just means, did it produce a lot or did it produce a little? But anyway, what it means is it didn't go the whole way. It didn't use up everything. Okay, so you started with some carbon solid plus some carbon dioxide gas, and it went to form carbon monoxide gas. So here's your recipe. 1:1:2. One of those plus one of those will form 2 of those. Okay. Anyone scared yet?
Mustafa says yes.
Who says yes?
Mustafa and Pascal.
Okay, Mustafa speaks for the whole class. The whole class is scared. Okay. And well, you might be. This terrifies teachers. Okay, define the term chemical equilibrium. Now, it's just explain what is meant by those 2 arrows. Do you see they're the same length? So what is meant by chemical equilibrium? It means the what reaction is equal to the what reaction. The forward reaction is equal to the reverse reaction. Everyone happy? That's what's meant by chemical equilibrium. So unlike our waffles, which can go back to form eggs and water and milk and all that, milk and flour, this reaction is a chemical reaction. Your waffles or CO can go back. But in my case, it was non-reversible. Okay, at equilibrium, meaning at the end, when you've done baking this whole waffle, it is found that the concentration of the carbon dioxide is 0.054 moles per decimeter cube. Do you recognize that concentration as the last column in our waffle columns? Do you recognize it? So here we got a concentration. So now we're going to do exactly the same as we did for waffles. We're going to do for carbon, carbon dioxide, carbon monoxide. Okay, so let's make a little table for it. And I've done that somewhere. Okay, won't you make a table like this? So carbon solid plus carbon dioxide gas goes to form 2 carbon monoxides. And frankly, if you ever get bored, just make a few more tables like this because we're going to do a few more today. By the way, the subject advisor only advised me this morning that there is no common physics paper. So that means more work for me. I've got to set a paper 1 and paper 2. Now, I don't know if that's good news or bad news, but let me tell you what will be in your paper. Okay?
So, how are we writing it? That's the question.
Are you guys busy writing this down? Is it okay if I talk while you write?
Yes, sir.
Okay, let me tell you exactly what is going to be in your September paper. It's probably the 29th of September that you're going to write, unless they change it. And then the 8th of October that you write paper 2, somewhere around there. You know what I'm going to do? I'm very good at cutting and pasting. So I'm going to go to 2017, 2018, and 2019 final papers. I'm going to cut a question from either of those papers. I'm going to change a few numbers, and there's your paper. So if you want to get 100%, just go over 2017's November paper, 2018's November paper, and 2019's November paper. And this is from, this one is,
Cited, sir.
sorry?
Where may we find these papers?
I will give you the link.
Okay, thank you, sir.
I just Google WCED, Western Cape Education Department, grade 12 past papers, but I'll give you the actual link.
Thank you, sir.
So this particular question could come in your paper.
What? Be the class.
Obviously, I just have to change a few numbers. Okay, what do we put in the ratio column here? What's the number in front of the C? It's an invisible 1. What's the number in front of the carbon dioxide? 1. And in front of the carbon monoxide? 2. So that's, but guys, just check that it's balanced. 1 carbon plus 1 carbon forms 2 carbons. 2 oxygens on the left, 2 oxygens on the right. It's always got to be balanced. I'm not sure that they will ever give you an unbalanced equation, but just in case, it's always got to be a balanced equation. Okay.
Yes, sir.
Now let's go and have a look at what did they tell us we started with. Initially, 60,8 grams of pure carbon dioxide. 60,8. So let's go back to the table. So under the carbon dioxide, 60,8 grams is what we started with. But you see, unlike making waffles, we work only in moles. So we have a formula to convert grams to moles. What is that formula?
Pascal.
What is
Pascal
the
says mass over molecular mass.
What is the formula?
Mass over molecular mass.
That's it, over the molar mass. So what is the molar mass of CO2?
Of what?
It's 12 plus 2 oxygens. So you just go to your periodic table and let's work out how many moles that is.
Pascal says 44.
Okay, I think someone's a lot faster than me with a calculator.
44. That's what Pascal said.
Okay, so that's 12, 2, 16, 32, 44. So what did you get then as 60.8 upon 44?
What? 1,38.
1,38. So that's how much CO2 apparently in moles we start with. All happy?
Yes, sir.
Okay, do they give us anything else that we started with? No. Okay. At equilibrium, it was found that the concentration of carbon dioxide is this. 0,054. And it was shared by 3 decimeters cubed. So let's go and do exactly as we did for waffles. Let's go and take 0,54 and put it in the carbon dioxide column at the end. Whoa, what happened there? Okay. Sorry, was that a concentration? Yeah, it's a concentration. So it's in the wrong column. Now, tell me, is anybody lost yet? I'm just taking what they're giving me and I'm finding the places on this table to put it. They gave me a concentration, I put it in the concentration column. Now, what I like about this is we've got to go from a concentration to moles at the end. We've got to convert that into something here. And there's the formula. Concentration is number of moles divided by volume. So what are we looking for here? N, C, or V here? Any ideas, guys?
Sir, repeat the question, please.
Okay, they gave us a final concentration of CO2, but here we need something in moles, right? We got to convert concentration into number of moles. How are we going to do it? There's your formula. So what is N equal to?
Multiply the concentration by the volume.
Well done, my geniuses. And they said the volume was 3 decimeter cubed. And there's the concentration. Okay, so it's going to be 0.054 times 3. And that tells us we end with 0.162 moles. So number of moles, to go from concentration to number of moles, we say concentration times volume equals number of moles, making number of moles the subject of the formula. So concentration times volume is moles. So we take the concentration times the volume, 3 decimeter cubed. There's what we end with. Okay, so who knows how we're going to work out this column here? We start with that, we end with that. We start with that, we end with that. How do we work out what was used up?
We subtract the one from the other.
Exactly. Okay, so give me an answer. If we subtract the one from the other, what was used up?
One comma 218.
Well done. Ezra, won't you ask anybody if they lost or worried to just tell me?
Is anyone lost? No one's lost, but Mustafa is a bit worried.
Okay. So, who can tell me how much CO we had to start off with? It's like, how many waffles did we have to start off with?
0.
So we always start off with 0 product. Now let's just go back to our waffle story. Did you see that if this is the ratio, we always use up and produce stuff at the same ratio as our ratio? Okay, this column's got to match that column. This has got to match that in ratio. So let's just go back to this ratio. If we have 1 here, the amount of this has got to be the same ratio as the amount of this. So what do you think the ratio of this is going to be? Or the number of moles of this is going to be? So 1 cup of flour plus 1 egg forms 2 waffles. So 1.2 eggs will need how many cups of flour? Or whatever. We got to keep this ratio the same, right? So who can tell me what this ratio is going to be? What this number of moles is going to be? Exactly.
1.218.
And who can tell me what this is going to be? Let's call it X. What is X equal to?
Pascal says he thinks 2,46.
He is right.
36.
Just let me show you a way that you could work it out. You cross multiply 1 times X. Unfortunately, I can't draw on here. I don't think I can draw on here. 1 times X equals 2 times 1.218. And you know that 1 times X is X equals 2 times that. So you say that times that equals that times that. You kind of cross multiply. And that's an easy way of giving you an answer. I hope that makes sense.
Yes, sir.
Okay, so the answer is going to be equal to 2 times 1,218, which is therefore equal to 2,436. Great. So can anyone tell me, if we start with no moles of that, this we make that, we subtract that. So how much of this do we end up with of CO? We start with naught, we make 2.4 moles. How much do we end with?
2,43.
Lovely. 2,436. Oh, whoops. Wrong place. Great. And who knows how we go from moles to concentration? How do we go from this number of moles at the end to a concentration? Well, what is concentration? C equals number of moles divided by volume, which is, we've got the number of moles, 2,436 divided by the volume is still 3. And that gives us 0.812. All happy? Does everyone understand what we did?
Yes, sir. Sir, can you just zoom in a bit, please?
Okay.
I go blurry. I don't ever know.
So just tell me when you've finished.
I see. Yes, sir.
Okay, now we've got to give the Kc for this. Kc equals products. Products. Concentration divided by reactants concentration.
Sir, can you zoom in? They cannot see at all.
Okay.
Please.
On this part.
Thank you, sir. Yes, sir.
Now, one peculiarity about KC is that when you have a solid, you ignore it and you turn it into a 1. So your products are going to be these things raised to their coefficient. Okay, so let's start with the first product, which is concentration of 0.054 raised to the power of what's its coefficient? 1. Times,
Sir, sir,
yeah,
sir, Pascal, or is it not 0.812? First, and over the reactants.
okay. It's these two are the product. These two are the products. Oh, hang on. I'm lying to you. My apologies. That should come over that. Yeah. There's your reactant. There were 2 reactants. Yeah. Okay. Sorry, I'm doing this wrong. So we got to put our product first. Well done. That's squared divided by our reactant. Which was raised to the power of 1. And we ignore the carbon, or in fact, you just say times 1, but it becomes a 1, the carbon. All solids and liquids don't have it. Their concentration is always 1.
All solids and
All
liquids.
solids and liquids. We only look at gases and aqueous. And here we've got 2 gases. So we only worry about the gases. So let's just go back to the question. So there's your Kc for this reaction. Let's just work it out as an answer. So we got 0.812 squared divided by 0.054. I get a Kc of 12,21 or 21. Yeah, 12,21. Do you guys see why we get that? It
Yes,
is
sir.
that raised to its coefficient divided by that raised to its raised to a coefficient of 1 times the solid, which has always a 1. So you can almost leave it out, and there you got your Kc for this reaction. Okay, so when you've got that down, let's just have a look at the question. I think they asked us to work out the Kc. They say, calculate the equilibrium constant for this, and it's 7 marks. What do you guys think of that for 7 marks? How much work
Nice.
was that? But was that good? Was it fun?
That's okay, sir.
Okay, so now let's have a look at how much carbon was used up minimum. Who can tell me how many moles of carbon was used up minimum in this reaction?
What? 1,219.
Yeah, we used up 1,218 moles. So who can tell me, it says here, the minimum mass of carbon that must be present. So we used up 1,21 moles of carbon. Will you guys be able to convert 1,2 moles to amount in grams for 3 marks? Shall we do that?
The answer is 14 grams. 14,4 from Pascal.
Well done. So you're going to say you're going to say number of moles equals mass divided by molar mass. Therefore, mass, little mass, equals n upon m. Sorry, n times n. N times big M. And we know the number of moles was 1.218 times the molar mass, which is 12, gives you
14,616.
14,616 grams of carbon used, minimum. And we worked that out from here. Now, how nice was that? 3 more marks. 10 marks out of 150 for this. Pretty sweet. And every exam, every year, they're going to give you a table like this.
What? What? Thank you.
So some people call this a rice table. Ratio R. Start, they say, is initial. C for change. E for end. And therefore you get a rice table. R, I, C, E, and then there's a concentration. So I think of cooked rice. C for cooked. Rice cooked. This is just a way of remembering it. Ratio R, start is initial, I, use or produce is how much it changes by, E for end, and then don't forget the last column, which is concentration. Okay, any questions there?
Any questions? No, sir.
Fantastic. Let me just look for another one that you guys can possibly do. Okay, let's have a look at this. It's always question 6. Carbonyl bromide, COBr2, decomposes into carbon monoxide and bromine according to the following equation. Initially, carbonyl bromine is sealed in a 2. We always must make note of the number of the volume and heated to 73. The reaction is allowed to reach equilibrium at this temperature. The equilibrium constant for this reaction is 0.19. Define chemical equilibrium. At equilibrium, it is found that 1.12 grams of this is present in the container. Calculate the equilibrium concentration of that and the percentage of that is composed at 73 degrees. Okay. So what we've got to do is we've got to create a table for this again. So let's do a table for carbonyl bromine. And I did do one somewhere. Let's just find it. I think I did one. Yeah. If you guys could just take that down. Ezra, won't you just tell me when they finished? Oops. It looks like we lost the class. What time does the lesson end? Maybe the lesson ended. Um, well, Matsdiso and Anis, did you learn anything from that? It was quite complicated, but did you learn something from that? Matsdiso, what did you,
Yes,
was it
sir.
okay?
Yes, sir.
There's nothing too awfully complicated, I hope, about it.
No, sir.
It's like, I call it physics Sudoku. It's basically just filling in the missing blanks. And Anis, I hope for the grade 10, our grade 10 student among us, there was a lot of new stuff there, but all of that is quite important stuff. So I think we'll continue with that problem next time. But yeah. Well, Matsdiso, I think we lost him. I'm not sure what time the lesson ends. Maybe they all walked out and I was just talking to myself, and you and Anis. It won't be the first time. I'm just going to press stop recording here.